डियर स्टूडेंट्स, वेलकम टू बिंदु धड़वाल केमिस्ट्री लेसन्स। आज का हमारा टॉपिक है गिब्स एनर्जी चेंज एंड इक्विलिब्रियम कांस्टेंट फ्रॉम द चैप्टर thermodynamics. Free energy is an extensive property and its value for a given substance will depend on the concentration of the substances. So just consider a general reaction, a reversible reaction. A plus B forms C plus D. The reactants will change to products and products can change back to reactants. For this reaction, the Gibbs energy of reaction is related to the composition of reaction mixture, that is Q, the reaction quotient, and the standard reaction Gibbs energy, that is standard free energy of reaction, with the relation delta G of reaction, free energy change of reaction, is equal to standard free energy change of reaction plus RT ln Q. Delta G R is the Gibbs energy change at a definite fixed composition of the mixture. Delta G naught R is the difference in standard Gibbs energies of formation of products and reactants both in their standard states. Q is the reaction quotient equal to ratio of concentration of products to that of reactants at any concentration. And R is the gas constant having the value 8.314 joule per Kelvin per mole. If the species are gases, in that case the concentration will be expressed in partial pressures and reaction quotient will be called QP. And if the reactants and products are not gases, their concentration can be expressed in moles per liter and reaction quotient will be expressed as QC, C for concentration. At equilibrium, this reaction quotient Q will become K, the equilibrium constant, where the ratio of concentration of products to that of reactant becomes fixed for a particular reaction. So then Q will be called as equilibrium constant, and at equilibrium the value of delta G of reaction will also be 0. This will be 0. So this equation will become 0 is equal to standard free energy change plus RT ln K instead of Q. So delta G naught R will be minus, this comes to this side, RT ln K, or if we change ln to natural log, then we get to the base to log to the base 10, we get delta G naught standard free energy change for reaction is equal to minus 2.303 RT log K. We can also write this expression in terms of exponents. K is equal to e raised to power minus delta G naught of reaction upon RT. This equation gives relation between equilibrium constant for any process and the standard Gibbs energy change, relation between K and delta G naught. We can also conclude that if delta G naught is greater than 0, it is positive, the rate constant will be less than 1, means product will be very less. And if delta G naught is less than 0 means negative, K will be greater than 1 means the concentration of products will be more. See, K is the ratio of concentration of products to that of reactants. If K is greater than 1 means products are more. We also know that standard free energy change of reaction is equal to standard enthalpy change for reaction minus T into standard entropy change for reaction. And we also know that delta G naught R is equal to minus RT ln K. So equating these two terms, we get RT ln K is equal to delta minus RT ln K is equal to delta H naught minus T delta S naught, and RT ln K will be, this will become positive, we bring it to the left side, T delta S naught minus delta H naught. So taking RT down, we get ln K is equal to T delta S naught R minus delta H naught R. T into standard entropy change minus standard enthalpy change divided by RT. For strongly endothermic reaction, delta H naught enthalpy change for reaction, standard enthalpy change for reaction is large and positive. In such cases, the value of K will be smaller than 1. This is large and positive, so this is small. So ln K will be smaller than 1 and reaction is unlikely to form products. In case of exothermic reaction, delta H naught is negative and large, so this value will get added up and K value will be greater than 1, means the reaction will go to completion and concentration of products will be high. Now standard free energy change also depends upon entropy change, and changes in entropy may also be considered. These changes will also affect the value of equilibrium constant and extent of chemical reaction, depending upon whether it is favorable to spontaneity or unfavorable. If it is positive, it favors the reaction. So we can have an estimate of standard free energy change from measurement of enthalpy change and entropy change, and then calculate equilibrium constant for any reaction at any temperature to get the economic yields of products. So before carrying out the process, we can get an idea of how much products we are going to get. And if we measure the equilibrium constant directly, then the value of standard free energy change can be calculated from this relation. So let's solve a numerical. For this reaction, the standard free energy change is given, the temperature is given, we have to calculate equilibrium constant. So we know the relation is standard free energy change is equal to minus 2.303 RT log K. So free energy change is given and R and T we know, so K can be calculated. Log K will be delta G naught R upon 2.303 RT. So a value of delta G naught R is 8.1, minus 8.1 upon 2.303 into R is 8.314 into 10 raised to power minus 3, and temperature is 1000. So solving this, we get log K is equal to 0.423 and K will be equal to 2.64. So from delta G naught we can find out K. Next topic is absolute entropies and third law of thermodynamics. We have studied earlier that the randomness or disorder increases with the increase in temperature. Entropy increases with the increase in temperature. It decreases with the decrease in temperature. So when the temperature is decreased to absolute zero, all the motion will stop and the disorder will not be there and entropy will become zero. So third law of thermodynamics deals with the entropy of perfect crystalline substances at absolute zero of temperature. When the substance is perfectly crystalline and there is no disorder, it's perfectly ordered, then according to third law of thermodynamics, at absolute zero, the entropy of a perfectly crystalline substance is taken as 0. This was given by Walther Nernst in 1906. इसका फ़ायदा क्या है? यूटिलिटी ऑफ थर्ड लॉ ऑफ थर्मोडायनेमिक्स, हम इसको लॉ को यूज़ करके हम प्योर सब्सटेंसेस की एब्सोल्यूट एंट्रोपी डिफरेंट टेम्परेचर्स पे निकाल सकते हैं. मान लीजिए कि टेम्परेचर T पे सब्सटेंस की एंट्रोपी S है. So if S0 is the entropy of substance at 0 Kelvin and S is its entropy at T Kelvin, then change in entropy will be S minus S0. But this change is also equal to integral of Cp delta T, heat capacity into change in temperature with respect to T within the limits 0 to T. Now since S0 is 0 according to third law of thermodynamics, so we get delta S is equal to S, or absolute entropy of a substance will be integral of Cp dt upon T within the limits 0 to T. तो ये जो वैल्यू इस इंटेग्रल की है, ये हम Cp अपॉन T को जब T के अगेंस्ट प्लॉट करते हैं तो उस कर्व की अंदर नीचे की एरिया जो है, द एरिया अंडर द कर्व, वो इस इंटेग्रल की वैल्यू देता है, और इस तरह हम सब्सटेंस का एब्सोल्यूट एंट्रोपी एट टेम्परेचर T निकाल सकते हैं. अगर हम एंट्रोपी जो है 1 मोल ऑफ अ सब्सटेंस की स्टैंडर्ड स्टेट में मेजर करते हैं तो उसको स्टैंडर्ड मोलर एंट्रोपी कहते हैं, और उसको S0m से रिप्रेजेंट करते हैं. किसी भी रिएक्शन की स्टैंडर्ड एंट्रोपी चेंज जो है, इट कैन बी कैलकुलेटेड फ्रॉम द डिफरेंस इन मोलर एंट्रोपीज बिटवीन द प्रोडक्ट्स एंड द रिएक्टेंट्स इन देयर स्टैंडर्ड स्टेट्स. यानी कि एंट्रोपी, स्टैंडर्ड एंट्रोपी चेंज ऑफ रिएक्शन विल बी सम ऑफ स्टैंडर्ड एंट्रोपीज ऑफ प्रोडक्ट्स माइनस सम ऑफ स्टैंडर्ड एंट्रोपीज ऑफ रिएक्टेंट्स, या सिग्मा स्टैंडर्ड एंट्रोपी ऑफ प्रोडक्ट्स माइनस सिग्मा स्टैंडर्ड एंट्रोपी ऑफ रिएक्टेंट्स. और अगर आपके जो Vp है स्टोइकोमेट्रिक कोफिशिएंट ऑफ प्रोडक्ट्स और Vr है स्टोइकोमेट्रिक कोफिशिएंट ऑफ रिएक्टेंट्स, तो हम स्टैंडर्ड एंट्रोपी को स्टोइकोमेट्रिक कोफिशिएंट से मल्टीप्लाई करके टोटल निकालेंगे, और उसके डिफरेंस को हम एंट्रोपी चेंज निकालने के लिए यूज कर सकते हैं. तो A मोल्स ऑफ A प्लस B मोल्स ऑफ B गिव्स C मोल्स ऑफ C प्लस D मोल्स ऑफ D के लिए हम इनके स्टैंडर्ड मोलर एंट्रोपी ऑफ C इनटू स्टोइकोमेट्रिक कोफिशिएंट C प्लस स्टैंडर्ड मोलर एंट्रोपी ऑफ D इनटू D, इनको ऐड करके, इसी तरह रिएक्टेंट्स को ऐड करके इसमें से माइनस करके हम निकाल सकते हैं. फॉर एग्जाम्पल, फॉर दिस रिएक्शन आयरन ऑक्साइड की वैल्यू है 87.4, तो इसको 2 से मल्टीप्लाई करेंगे, और माइनस 4 इंटू आयरन की वैल्यू है 27.3, ये प्लस 3 इंटू ऑक्सीजन की वैल्यू है 205.0, ये सॉल्व करके हमारा आंसर आ रहा है माइनस 549.4 जॉल्स पर केल्विन पर मोल. This is all about thermodynamics. Thank you. Have a nice day.